So today we're doing a demonstration of speed, distance, and velocity. Now first we have to define these three terms. First, we'll start with distance. Distance is the amount of space between two objects if we were to travel in a straight line. So for example, from this car launcher to this clock, the distance is 75 centimeters. So now we have distance defined. What is speed? Speed is the distance an object has traveled divided by the amount of time it takes it to travel that far. So if we were to launch this car, the speed is the distance it has traveled divided by the time. So that's speed. But what is velocity? Well, it is similar to speed, but it's the displacement of an object divided by the amount of time it takes to travel. Displacement is different from speed because instead of the displacement is different from distance because if we had launched this car, it might have go here, swerved, and turned. This is the displacement, which is still the object to the origin. But if you look at speed, like this distance that the car has traveled, we're counting this part, going here, turning, and all of this distance that has run with like, if we were to put a point, on this car. So now we have all three terms defined. So now we're going to calculate the average speed, distance, and velocity of this car if we were to launch this at a random point on this table. We're marking this point as the origin, and so we're going to get our stopwatch. 3, 2, 1. So it took 1.15 seconds, about 1.15 seconds to travel to this point. And since it's traveling in a straight line, the displacement and the distance are the same. So if we measure the distance from the car to the launcher or origin, we'll see it's 66 centimeters. So 66 centimeters divided by 1.15 seconds for it to take. We go that far, and we get 57.39 centimeters per second. So this time we're going to repeat the experiment, but we're going to add an obstacle in front of the launcher so that the car hits it and bounces off, and change the direction so that the displacement and the distance that I've traveled will not be equal. So we're going to launch in 3, 2, 1. Alright, so it took 0.83 seconds to travel to here. Now, first let's calculate this distance that it's traveled. So it traveled from here, hit this point on the obstacle, and then moved here. So we're going to measure the distance from the launcher to the obstacle, which is 15 centimeters. Then we're going to measure the distance between the obstacle and the car, which is 19 centimeters. So 15 plus 19 is 34. So 34 divided by 0.83 seconds. And we'll get 40.96 centimeters per second for the average speed, but the average velocity is different. So it still took 0.83 seconds, but the velocity is measuring the distance between the origin and the car. So it's 26 centimeters instead. So 26 divided by 0.83. 26 divided by 0.83. and we'll get 31.33 seconds on that. 31.33 centimeters per second for the velocity. So we're going to repeat this experiment one last time, but this time the car is going to hit here and fall off the table, making the displacement a three-dimensional vector. So 3, 2, 1. So it took about 1.45 seconds to travel here. And since it traveled and went here and then bounced off and here, that is, we're going to measure the distance travel first. So it traveled 13 centimeters before hitting the obstacle and traveled 79 centimeters while falling. So 79 plus 13. 79 plus 13 is 92. And then we're dividing that by 1.45. So we'll get it traveled 63.45 centimeters per second on about 63.45 centimeters per second. And if we're measuring the speed, but velocity, we're going to measure the straight line from the origin to the car, which is 81 centimeters. So 81 divided by 1.45. And we'll get 55.86 centimeters per second on average for velocity.